This meeting is being recorded.
Oh, you're welcome, Henrik.
Okay, thank you very much for the invitation. It's really nice to learn about your seminar and the people that come here. So I really appreciate it, and I hope that I will talk here again in the future as we discussed. So I'm going to talk about jets and differential operators and non-commutative geometry. This is a project which I started while I was in Brno together with Keegan Flood and Mauro Mantegazza. None of us are in Brno anymore, but the project is still ongoing. And okay, let's talk about what I think non-commutative geometry means, because there are some different philosophies about what you should actually be trying to do. So let's say that we are studying geometric objects, usually in normal geometry, via some algebra of regular functions, for example, smooth functions on a manifold, or algebraic varieties via their ring of algebraic functions, modulo some ideal, or so on. And what we want to try to do is construct geometric objects using only these algebras of functions. And then we also want to try to generalize these commutative algebras to associative unital algebras, which are not necessarily commutative. We don't actually demand that they are non-commutative, as the name might suggest, just associative unital and not necessarily commutative. And when you do geometric constructions, if A happens to be a commutative algebra, then you should reproduce the classical object that you're trying to generalize, of course. This is an important guiding point to me. And working just with the algebra function and forgetting about the space sounds difficult, but there are results from the classical geometry, such as the Gelfand-Naimark theorem and the Searles-1 theorem, which shows that it's not impossible to work in this way. So let us try. So in our setting, we're going to go to associative algebras, and we're going to need some way to encode some kind of smooth structure. Just working with an algebra is not going to be enough. We need to think about something we could call differentiable algebras. So we're going to borrow some notions from quantum groups, or at least as far as I know, they originally arose in quantum groups. These are
I'm sorry, you need from your algebra just unitality, yes?
Yes, just unitality and associativity.
Okay.
And then we're going to borrow some extra structure. So we're going to equip this algebra with some extra structure, an exterior algebra and a first order differential calculus. So in particular, this lets us work in other frameworks that has some notion. I should say, don't be worried about asking questions along the way. It should be enough time to answer.
I'm sorry. And in your second condition, you don't have brackets about D from B. There must be brackets about in first term.
I did not understand, sorry.
Your second condition, A B module, and second one, that D from AB, it's equal to A multiplying what? D from B, yes? There must be brackets about DB.
Sorry, I didn't get to the definition yet. So
okay,
give me 1 second and I will explain.
Okay.
So anyway, the geometries that we have in mind when generalizing this are classical differential geometry, supergeometry, what I call quantum geometry, which includes stuff like braided Hopf algebras and quantum homogeneous spaces, and also a lot of toy examples. Okay, so let's talk about the definition of a first order calculus. So a calculus for a unital associative algebra is a bimodule and a bimodule valued derivation satisfying a surjectivity condition. And now, sorry, could you please ask the question again?
Okay, again, you have got on the right side of this equality, which looks like Leibniz rule.
Yes.
First term, A, D, B.
Yes.
You have got brackets around D from B or no?
DB has a bracket, yes, indeed.
Oh, okay, thank you.
Okay, so the surjectivity condition just states that the image of this differential actually generates the calculus by taking finite linear combinations. But there could be infinitely many generators. This is not assumed.
And I'm sorry, again, another question.
Yeah.
You can put AB from where? AB from A?
A, yes. So it's a map
And the
from A.
multiplication on the right side is the multiplication from a bimodal structure, yes?
This is the bimodule structure, indeed.
Okay.
Okay, so we're going to make some change of notation from classical geometry and translate to algebra and then to non-commutative analogs. So in geometry, you have points. In algebra, you have fields. For our non-commutative setting, it's going to be enough to work with commutative rings. From geometry, you have manifolds. On the algebraic side, you have smooth functions on this manifold. And the non-commutative analog is just going to be a unital algebra over your ring. For a vector bundle, the algebraic object is the space of sections. And for the non-commutative side, we're just going to take a module E, which is a finitely generated projective left A module. Those will be thought of as our vector bundles. Okay, so in general, you can have bundle maps as well between these. On the algebraic side, these are maps between sections, and they will just be left A linear maps from our setting. And finally, you can think about the cotangent bundle. On the algebraic side, this is one forms. It's just a special case of the previous, actually. But on the non-commutative side, this is going to be the first order calculus. That we haven't picked it yet, but that's going to model it. Okay, we will introduce some notation for the categories of right and left A modules. They will be called A mod and mod A for left and right respectively, and bimodules will be called A mod A. Then we will introduce a notation for some important subcategories. So the subcategory of flat left modules is called A flat. Projective is called A proj, and the full subcategory of finitely generated projective left modules is called A FGP. Okay, so I don't know how much this audience knows about classical jet bundles. So let me just give an idea of what they are. So if you take a vector bundle in classical geometry, then the associated nth jet bundle represents the bundle of nth order approximations of sections of E, but in a pointwise way. So these are actually in the fiber equivalence classes of sections up to nth order contact, which I will not explain more carefully now because it would take too much time. However, you can think of them as Taylor series, which are defined in a coordinate independent way. So it's an intrinsic notion of Taylor approximation up to order n. They also provide a way to characterize differential operator, an intrinsic definition of differential equation, and a tool for a theory of differential equations, so geometric PDE, for example.
And what is the definition of nth order? What does that mean?
You can think of it as something that depends on up to nth derivative at the point. That would be the nth order jet at that point.
Is it possible to write that definition? Because I think it will be very important in future. Or you can just talk it again if possible.
Definition of nth order contact.
Yes, if it's possible, of course.
It's actually going to take some time to do that, so I would rather not, if you would be okay. It's really just for motivational purposes. So I will not depend on the technical details of this.
Okay, the next time we will like to see.
Okay, my apologies. I will tell you about it next time.
Okay.
Okay, So we want to take the non-commutative setting that we described on the lexicon page, and we want to augment it with jet constructions, differential operators, and differential equations. The method that we intend to do this is to use the categorical and algebraic structure of jet modules and jet functors, prolongation maps, and projections, which I will tell you about now. So if you have a vector bundle and you map it to its nth jet bundle, and this is an additive endofunctor on the space of vector bundles, on the category of vector bundles. That's already saying something because you need some way to make sense of what happens to the morphisms. And if you pull through this source1 correspondence, then this gives you an additive endofunctor on the space of sections of vector bundles on the finitely generated projective C infinity M modules, so modules over smooth functions on the manifolds. And importantly, these jet functors come equipped with natural transformations. First is the jet projection, which lowers the jet order. So pi mn goes from jm to jn, where m is greater than n. And then you have the prolongation map, which goes from the identity functor to the nth jet functor. So that takes basically some section to its section of equivalence classes to nth order contact, which again, I'm sorry I did not explain. And importantly, this jet functors satisfy a exact sequence in the category of endofunctors. So on the left side here is the functor of symmetric forms on your manifold with values in whatever bundle you started with. And this is injected into the jet bundle. And the projection then goes down to the jet bundle of one order lower. And this is exact, so these forms with values in your bundle are exactly the kernel of this projection. And finally, if you compose the jet prolongation and the projection, then you get another jet prolongation. Of course, these superscripts have to make sense. M has to be greater than n. Sorry, n has to be greater than m. So we want to generalize this picture. So what should we require from such a generalization? Well, first it should be an endofunctor from A modules to A modules. Okay, and the jet bundle of a vector bundle is again a vector bundle. So you should try to preserve the various subcategories that we are interested in. For example, finitely generated projective. It should fit into some jet exact sequence. So you should have these natural transformations, pi, and the kernel of pi should be a naturally included subbundle of something like forms with values in your bundle, which we will construct with the tensor product functor with our notional differential form, which is just a calculus pi module. And again, this jet prolongation, which provides a splitting of the sequence in the category of left modules. No, sorry, not left modules. Actually, not in any category in general. But it splits the sequence as k modules. And the jet projection and the injection of these forms into the one jet module should all be natural transformations. Okay, so these are all important requirements. Let's see what we can get if we demand them. So first, there is a universal calculus for any algebra, which depends only on the algebra itself. It's given by the kernel of the multiplication map as the bimodule. And the universal differential is given by taking some element A to 1 tensor A minus A tensor 1. So remember that we're unital, we have 1 available. And of course, if you apply the multiplication map to this, you get 1 times a minus a times 1, so it's 0. So it's in the kernel. It's actually well defined. It satisfies the Leibniz rule, and this is also surjective. So it generates this kernel. In particular, we can write the following exact sequence. You can go from 0 to the universal calculus to a tensor over ka, and then to a, just using the multiplication map. And the multiplication map is a bimodule map, so we are simply going to use that as our universal projection. Take a tensor b and map it to a times b. The universal calculus is embedded naturally in a tensor a just by construction. Okay, so that's also natural. And finally, we need some prolongation. And for that, we will take the map J1U, which takes a to 1 tensor a. Very simple, and it splits the sequence as a right module, but not as a bimodule or a left module. And I may remind you that this is just for one particular module and one particular calculus so far. We have not constructed any functors yet. Okay, but there is a reason that this is called a universal calculus. And that's because if you have any other calculus, then there is a surjective map from the universal one. This is a bimodule map. And it intertwines the differentials. It takes du to d. So in particular, you can write the following exact sequence. You take nd for some bimodule, which is the kernel of this PD, and you have a surjective map into omega 1d. And this is for some sub-bimodule in omega 1u. Okay, so if we are dealing with actually the calculus omega 1d, then we are going to call nd the space of first-order differential relations for that calculus. So in particular, if we are dealing with classical one forms, then these first-order differential relations will contain things such as, in local coordinates, du of f minus the partial derivatives of f in the usual sense times du of the part of the coordinate functions. So this looks very similar to the generators of the Cartan distribution, and it will play a similar role for us as remembering the relationship between formal variables and their actual differentiation in this theory. Okay, so let's say that we want to have the jet exact sequence for some module. So here's the universal jet exact sequence again, which we defined for the module A in the previous picture. So now let's say that we also have the omega 1d, and
it's
now,
an embedding from omega 1 to G1.
Yes, it's an embedding, right. It should always be so because it's exact sequences.
It's a natural embedding or no?
It will be a natural embedding, yes.
Okay.
Okay, so by the previous consideration, we have a map going from omega 1u to omega 1d. This is called PD, and it's surjective. That's the universal property of universal calculus. And also we have A is equal to A, so that's just an equality. And then, because A is a very nice module of itself, or over itself, this sequence always splits. So you can always find the splitting. So we have some map from J1u to J1d, no matter what. Okay, let's try to explore more of this to find out what J1d has to be. So we introduce kernels and co-kernel sequences. And then we know from the universal property again that the kernel sequence is exactly nd for omega 1u, and we don't know yet what the kernel of p hat d is. But since we have this situation, it's exactly the one that we need to apply the snake lemma. So we do. And now you know that the long sequence going through the middle is also a long exact sequence. And since this sequence has many zeros, we can deduce some isomorphisms and other zeros. So the bottom co-kernel has to vanish, and the map from ND to kernel of P hat D has to be an isomorphism. Okay, and now we are basically done because this is a short exact sequence describing J1D. We just need some extra description. You can now identify ND in the top line. They are isomorphic and mapped to each other, so why not? And then you can write J1D as a quotient of A tensor A over K. So this is how it has to be, and what about the prolongations? Well, you have the universal prolongation that we constructed earlier, which splits the sequence in the category of right modules. You can simply push this down to the bottom and get the jet prolongation in the category of right modules as well. So this is the jet module. We define the jet module of A as A tensor A mod key over K modulo ND, so modulo the space of differential relations. And the projection is just going to be the multiplication map. This is well defined because ND was precisely contained in the kernel of the multiplication, so it doesn't depend on which class you choose. The square brackets are always classes here. And finally, J1D is just the one that we push down, the class of 1 tensor A modulo differential relations. So now, in order to obtain the short exact sequence for all E, which we can just apply the functor, which tensors with E as a left module. So the one-jet sequence also splits in mod A, so it remains exact. But we can do it slightly better than this. So analogously for the case of A, for any left A module E, we define the space of differential relations by these equations here. So if you take the product map that just uses the module action, then you should get 0. And moreover, if you tensor with the differentials, then you should also get 0. And this will be a submodule of A tensor E. So let us define the one-jet module for a left A module E as the universal one-jet module of E, quotiented out by these differential relations. So A tensor E over K modulo first-order differential relations for E. Okay, and then similarly, we define the prolongation operator for E by the class of 1 tensor E, and the projection map will be the map that applies the module action. Once again, it's well defined for the same reason. And this is consistent with the construction for the previous slide. Okay, so that gives us the construction. We also need to lift morphisms. So let phi be an A-linear map between two A modules. Then we define the image of the one-jet functor as the A tensor of the identity map on J1A and phi. And this will be a map between J1D and J1F. So this is now a functor. So then the theorem is that this construction gives you an additive endofunctor on the left A modules, which realizes our prolongation and projection constructions as natural transformations to and from the identity functor on the left modules, respectively. In the category of additive endofunctors, we have this exact sequence that we actually wanted for a one-jet functor. Okay, and moreover, if omega 1D is flat, or respectively projective or finitely generated projective, then this functor preserves these subcategories. So they preserve the flat subcategory or the projective or the finitely generated projective one. And this latter fact is geometrically comparable to that the jet bundle of a vector bundle is again a vector bundle. It's not something more general. Okay, so let's outline what we're going to do for the rest of the talk. we're going to construct three families of functors. The
I'm also
non-holonomic.
sorry.
Yes.
Can we return to the previous frame? Can you give some examples of application of your theorem in practice? So I mean that what it means, for example, for if I take as a bimodal, for example, L1 functions over group algebra, then what that will mean, this theorem for such
The important
examples?
part is not which module you take. That doesn't really matter. The important part is which differential you take. So what is your differential going to be?
We can do, for example, inner derivation.
Some inner derivation. Yes, this has some interpretation, which I will talk about later. The inner derivations are related to something called a terminal construction. So it will generate basically the smallest geometry for which the left multiplication by the generator of the inner multiplication is a differential operator of order 1.
Okay, and if I take not inner derivation, but some outer derivation?
Well, then it's fully general. I don't know. I'd have to look at it.
Okay, thank you. Okay, thank you.
Okay, so we are going to construct three families of jet functors, which we call the non-holonomic, semi-holonomic, and holonomic jet functors. And most normal people just call the holonomic jet functors the jet functors. Don't be scared by the name. It's just that we need to distinguish all these jet functors in this talk. So the holonomic jet functors is usually the one that you actually want, although the other ones appear in the literature as well. And for us, they will be important for making constructions. For these, we always have that the zero order jet functor is the identity functor. And the first order jet functors always coincide with what we saw on the previous pages. And the nth order functors also come equipped with natural transformations, projections, and prolongations, which are called non-holonomic, semi-holonomic, and holonomic jet prolongation and projection maps, which have the properties that you want. So if you compose a projection and a prolongation, you get another prolongation, for example. So the first and easiest is the non-holonomic jet functor. You have a functor that takes left A modules to left A modules, then you can iterate it if you want, right? No problem. So if you do that n times, you get the nth non-holonomic jet functors. And this is, of course, also an endofunctor. And you can make a non-holonomic n-jet prolongation by taking the component of the jet prolongation at each value of the jet functor and composing them appropriately. So you take J1 times J1 applied to J1 times J1 applied to J2 and so on n times, and then you will get some non-holonomic n-jet prolongation map. And also you have not one, but you have many epimorphisms that go down one layer. They are labeled by M, where M is from 1 to, including 1 to n. You have natural epimorphisms, which are called non-holonomic n-jet projections. And this is not so good because ideally you would like to have only one jet projection. So let's take care of that next. If you simply take all these jet projections and take their equalizers, then you get another functor. So that is the functor of some subfunctor on which all of the projections coincide. So in that case, since they all coincide, you have one unique natural transformation, which we'll call the semi-holonomic projection. And the semi-holonomic projection is still not quite holonomic, but it's also geometrically important in many contexts. For example, it can be used to measure curvature of certain objects. Okay, so here is a proposition that says that the prolongation actually factors through the semi-holonomic jets. So if you take a jet prolongation of some element of your module E, then the prolongation will actually take values not in the non-holonomic jet, but in the semi-holonomic jet, which is contained in it. And this is just a proof of that, but let's not discuss it too long. And finally, the semi-holonomic jets also have their own short exact sequence. And now we need some assumption. Let's say that the calculus that we started with is flat as a right module. Then you have this short exact sequence, which is not exactly the holonomic jet exact sequence, because the tensors over the one forms are not symmetrized. So you will get unsymmetrized tensors with values in whatever your module is. But nevertheless, it's some property that it has. And sometimes the semi-holonomic jet is actually what you want. Usually you want a holonomic one though. So let's move on and try to refine this further into the holonomic jet functor. And to define the holonomic jet functor, we're going to need slightly more tools. Now, these are not our definitions. It's again things that we borrowed from quantum groups. So this definition of exterior algebra in particular is not original to us. But an exterior algebra is an associative graded algebra, which is equipped with a map D, a differential. So it's a differential graded algebra, which is generated by degree 1 and degree 0. That's another surjectivity condition. And in general, if you take another differential graded algebra, you can just take this sub-differential graded algebra, which is generated by this, and you will get something which satisfies this condition. So it's actually not too bad a requirement. Now, these will play the roles of higher degree differential forms on our manifolds. But actually, this does not need to be considered as extra data. It can, but if you have an exterior algebra, then the first grade and the differential form a first order calculus. And on the other hand, if you have a first order differential calculus, then there exists a maximal exterior algebra, which has a universal property that any other exterior algebra for that first order calculus quotients through it. And this one is just given by quotienting the tensor algebra over omega 1d. So omega 1d, tensor over A, omega 1d, and tensor over omega 1 over itself, with the tensor product as the algebra operation, by some relations. And these relations are precisely the minimal relations that you need to have d squared equal to 0. So normally, we are only interested in the maximal, this maximal exterior algebra. It's also called the maximal prolongation. And by the way, in the classical setting, the exterior algebra on a manifold, the differential forms of the manifold are formed by taking the maximal prolongation of the one forms. So at least classically, this turns out to be the right thing to do, and usually in noncommutative geometry, it's also the right thing to do. Okay, but now comes a definition which is due to us. So in the classical case, to define the holonomic jet exact sequence, you need the symmetric forms with values in your bundle. So in that case, in the classical case, it can be seen as a tensor product bundle. And in this case, we will also try to define it as a tensor product bundle. So let us take our exterior algebra, which may be just a maximal prolongation of the first term. And we define tensor product functors by taking left tensors on left modules. Then we define the symmetric, the quantum symmetric forms. I should say I'm using the term quantum symmetric forms, not because it has something intrinsically quantum to it, but because I want to emphasize that these are not symmetric in the classical sense. Like you don't have that AB is equal to BA or something like that. It can be more complicated. Okay, so let's define the functors S0 as the identity functor, S1 as the tensor functor of omega 1. And for n greater than or equal to, should probably say 1 there, not 0, we take the kernel functor of a certain composition. So we take the kernel functor of composing Sn minus 1 with omega 1. So you get n minus 1 entries which are already symmetrized and one extra one. And then you apply the wedge map to them. And then you'll go to omega 1, and then n minus 1 symmetric components. That's just by injection. You didn't really do anything, but then you can wedge those two components. So basically, you take the kernel of the antisymmetry. And if you do this iteratively, then you will get the nth degree functor of symmetric forms. And now this iota is just the inclusion of Sn into omega 1 times Sn minus 1. So that one is canonical. And this is our definition, and it's good for our use for many reasons. But there are other definitions you could think of for a notion of symmetric forms, which are generated by the calculus. And if omega 1 and omega 2 are flat as right modules, then all of these reasonable definitions coincide. So, for example, you could take the intersection of applying the wedge operator to each argument, or some more complicated things. TK here is just the k-fold tensor product over A of omega 1 with itself. In any case, they all turn out to be the same if you have this flatness condition, which is really a very minimal homological condition to demand. Okay, now let's define the Spencer operators. So take some left module, then we will define the non-holonomic Spencer operator as the natural transformation with component at E, which goes between the omega 1 times omega m minus 1 times j n minus m plus 1 functor to the omega m times j n minus m functor. And that sounds very complicated, but actually it has a very simple formula. You just take one entry from your jet and you split it up because inside the bracket is a k-fold tensor product. And then you apply D and left multiplication on the form part and the jet part. So notice how the form degree raises by 1 since you remove the plus 1 when you apply it. This is actually well defined. And you can define the semi-holonomic, sesquiholonomic. I didn't explain what sesquiholonomic is yet, but wait for that. And the holonomic Spencer operators analogously. Okay, so in classical differential geometry, the Spencer operator is also important, but it has a more complicated formula. If we take that formula and write it down in our setting, you will get what's on the bottom of the page. And in fact, we can show that this just coincides with the simple formula that we gave on the middle of the page. But of course, this simplification relies on using our square bracket notation, which is helpful. So I remind you, the square brackets means take the quotient by differential relations. Okay, so we also need to define the Spencer cohomology. It will be needed later. So we can consider a different map. And actually, this is related to the Spencer operators that we defined earlier, but you cannot quite see it at the moment. But this a natural composition of natural transformations. So take omega 1 times symmetric forms of degree 1, omega k times symmetric forms of degree k, and then inject them into omega k times omega 1 times s h minus 1 using the natural map iota from the construction. And then apply the wedge map to increase the form degree by 1 and decrease the symmetric degree by 1. So this is called the Spencer delta map, this whole composition with index h and k. And in fact, this gives us a complex in the category of functors of type A mod to A mod. And the cohomology of this complex is called the Spencer cohomology. The complex itself is called the Spencer delta complex. Now, usually in classical geometry, this complex has zero cohomology. Or you can equivalently see this as being the Spencer cohomology of the empty differential equation. Usually the Spencer delta cohomology is applied to some differential equation, and then it will be non-trivial. But in this case, non-commutatively, it's not clear that the Spencer cohomology of the empty differential equation is zero. So it's not clear that the empty differential equation is automatically involutive. And if it's not, then its Spencer cohomology will be this Spencer cohomology. We are going to need this cohomology at the level hk later on. Okay, so now take once again the non-holonomic jets of order 2. Construct a non-holonomic 2-jet Spencer sequence. This sequence is not a complex in general. And even if you restrict to the semi-holonomic 2-jet, this is not in general a complex. So we can define the holonomic 2-jets as the maximal subfunctor of the semi-holonomic 2-jet, such that the sequence is in fact a complex. So you will have J here, and we have removed the brackets around the 2 to indicate that this will actually be the holonomic one. Okay, and this definition may seem a bit strange, but it does have some benefits in that it requires no algebraic conditions on our data to make sense. But we can also describe this holonomic 2-jet more explicitly. But for that definition to make complete sense, you need some assumptions. So let's say that we want to consider the 2-jet exact sequence now. We want to consider something that fits into it. So you want something which admits an injection of the quantum symmetric forms of degree 2, and admits a natural transformation into the 1-jets. And this should be an exact sequence. We can consider the 1-jet sequence of the 1-jet. This can be related to the non-holonomic 1-jet. So the 1-jet applied to the 1-jet is just the non-holonomic 2-jet. And the 1-jet at the right-hand side is just the same, so that's just an equality. And finally, we have a natural mapping from the quantum symmetric forms of degree 2 into omega 1 times J1 also. So we can write it like this, a morphism of sequences. And then to go further, we should think that omega 1 is flat as a right module. And the jet prolongation agrees with the non-holonomic one.
I'm awfully sorry, perhaps I cannot see, or perhaps I cannot understand what is written on the left arrow, which goes from s squared to omega 1.
So first you inject S2 into the place where it's defined, which is omega 1, tensor omega 1. Then you apply the omega 1 functor to iota 1 applied with component on D. So this will just embed omega-1 tensor omega-1 into the omega-1 that's inside omega-1 applied to J1 omega-1, because J1 contains a subfunctor omega-1 as well. Does that make sense?
I think yes.
Okay, great. So it's just composing natural things that we get by construction, basically. Okay, so under these conditions, that omega-1 is flat as a right module, then you can just take the direct sum, not the direct sum, but the sum of the module generated by prolongations to degree 2, non-holonomic prolongations, and the symmetric forms, quantum symmetric forms of degree 2, inside of the non-holonomic 2-jet module, and they will satisfy the short exact sequence. And in fact, it turns out to be, regardless of assumptions, the same things that we constructed by the Spencer operators earlier. So this is another possibility that you might use to define it. And finally, there's one more way to do it. We can describe J2 as the kernel of a left linear map, which we call EV. I guess Lea is Vietnamese, so you might recognize the letter. Actually, we got it from Norse. So EV tilde, which maps a non-holonomic 2-jet into some special module. And this special module I should describe first of all. So this omega-1 semi-direct omega-2, first of all, as a right module, is just a direct sum. Then to define it as a bimodule, you should describe the left action as well. And the left action will be a left action which is twisted by the differential. So if you have something that's written as A plus alpha plus omega in the splitting, then F left multiplied on this should give you F times alpha plus the differential wedge alpha plus F omega. So it's a twisted bimodule. And then explicitly we have the map given by the formula at the bottom of the page. And this this operator actually turns out to be the jet lift of a differential operator. And it turns out to be important for proving that the classical limit of our construction is correct. And also it has a very simple form in 2 components. You could split it up into components, but if you do, the second component is not well defined unless the first component vanishes on some element. So actually the first component measures semi-holonomicity. And if both components vanish simultaneously, then your section is actually holonomic. So if you apply this to something. But of course, it doesn't make sense to ask for only the first component, because then you would be asking for semi-holonomicity, for holonomicity without semi-holonomicity, and that's just not possible. Okay, so now we can give 2 equivalent definitions of the holonomic n-jet functor. Either you can promote this EV operator to actually give you something on J1 times the Jn-1 jet. Then it will go to this special module times Jn-2. And its kernel will be the holonomic n-jet functor. Or you could generalize the Spencer definition, and you take the maximal subfunctor of something called the Sesky holonomic n-jet functor, which I have not introduced yet, but I will in a little while, such that the following sequence is a complex once again, so very similar to the Spencer 2-jet definition. And as it's written in the middle of the page, these 2 definitions are actually equivalent. Okay, so then we need holonomic jet projections. And they are more or less given in the obvious way. You just modify the projections that you already had, and this will give you what you need. So you had some for the semi-holonomic and non-holonomic, and they will basically restrict, and you get the projections that you want. And we can also compose things to get the projections from any order to any lower order. Okay, and for a prolongation map, it's a bit of a lemma to show that the non-holonomic prolongation map, in fact, takes values not only in the semi-holonomic jets, but in the holonomic ones that we just constructed. But it's true, and you can show this by using the Ev tilde operator that we constructed as an alternative definition. Okay, and now we come to one of the main results that I wanted. If you have sufficient algebraic regularity of your ingredients, then you get the n-jet exact sequence. So in particular, you should demand that omega 1, 2, and 3 are flat as right modules. And in addition to this, for n greater than or equal to, well, should actually be 2, the Spencer cohomology at the value, at the gradation n, 2 should vanish. For all m smaller than n minus 2, then we have the jet exact sequence. And this is important in particular if you want to have good properties for the values of the jet functor as representative objects of differential operators, which we'll get to shortly. If you don't have something like this, then you can more or less forget about having good properties. Okay, so let's prove this theorem, but then I will have to introduce one more jet functor, which is not like a headliner main goal of us, but which we just use as a tool for proving different things. So this is called the sesquiholonomic n-jet functor, and it's a bit more esoteric, but it is known. Yes? Okay, sorry. It's a bit more esoteric, but it is known in the literature. In particular, I think Lieberman writes about this in the classical setting. So in any case, we need it's a subfunctor of J1 times Jn minus 1, which is defined as the kernel of this operator. And what this means is basically that it's this is not the Ev tilde operator. It's just the first component, which I said was defined independently. So what this means is that you take jets which are holonomic in all orders except for their leading order. They're only semi-holonomic at leading order. But being holonomic in all other orders and being inside the semi-holonomics means that the jet projection is actually uniquely defined. And therefore, actually, when you take the jet projection of a sesquiholonomic jet, you get a holonomic one. Also, of course, by construction, it comes with an inclusion into J1, holonomic J1 times Jn minus 1. Okay, so now if the holonomic, you have this flatness condition for omega 1, and then you can lift the holonomic n minus 1 jet sequence exactness to sesquiholonomic n sequence exactness. This is important because it allows you to lift exactness by one jet order, although to the wrong functor, but still, it's going to be a stepping stone for us. And also, Ev1 remains surjective, somehow an important observation. So you get the sesquiholonomic n-jet exact sequence if you have the n-1 jet exact sequence for the holonomics. So I don't want to carefully go through the proof of this, but it's basically a chase through homological algebra and the following diagram. All the arrows are just compositions of things that we made by construction. So it all works out by just verifying this. Okay, so what I do want to spend a little bit more time on is to see where the Spencer cohomology interacts with the with the jet sequence. So by construction, you always have this natural inclusion of the jet sequence into the Cesky holonomic jet sequence. So the kernel of the Cesky holonomic projection is omega 1 times Sn minus 1. And of course, you have a natural inclusion of Sn into this by construction. So let's do homological algebra to it. So first, you can continue the sequence vertically by considering the wedge map. As we did before, you consider this Sn minus 1 as being inside omega 1 times Sn minus 2, and then you wedge. And you can also do Ev tilde times the appropriate functor and go into this special module times Sn minus 2. So actually, since the Cesky holonomic jet is semi-holonomic in particular, one component vanishes. And so you can consider this as being a map into omega 2 times Sn minus 2, which is nice because it's what we have right next to it on the left in the bottom row of the diagram. So let's add a 0, and this is basically fine. You have two modules which are equal, okay. And then we recognize that the wedge that we wrote on the left-hand side earlier is in fact the Spencer delta operator. Because actually, as I explained, it's two compositions that precisely define the Spencer delta operator, although with a sign, but it does not matter for purposes of computing cohomology. So it goes into the kernel of some other Spencer delta operator, and that one has a surjective map into the cohomology that we wanted. And now it's a matter of completing the diagram. You get some extra co-kernel for the term to the right in the middle column. Let's just call it C. It's completely irrelevant what it is. But the point is that the long arrow going through the middle is now a long exact sequence. And so you see that, in fact, unless this long snaky arrow is the 0 arrow, it is absolutely impossible to have the jet sequence be exact. So the easiest way to get it to be non-exact is to say that this cohomology is actually 0. So that's what we do. So if you do that, then the long exact sequence will actually be a short exact sequence since it ends with 0 after 4 terms. And that is the reason why you can't have the jet sequence be exact without vanishing Spencer cohomology. Okay, so let's talk about another theorem, which I will not prove, but which is kind of important. You take your first order calculus, and we want to see that actually the jet functors preserve the appropriate subcategories that we were interested in. So the flat modules, projective modules, and finitely generated projective modules. And the non-holonomic jets preserve these if omega 1 is flat as a right module. Okay. The same, more or less, is true if you have a flat as a right module omega 1, or respectively projective or finitely generated projective, then the semi-holonomic jets functor preserve these subcategories, respectively. Now, for the holonomic jet, you need to demand a bit more. So let's consider the exterior algebra and say that omega 1, 2, and 3 are flat as right modules. Notice that this is the same thing that we need for the jet exact sequence. Now, if you have vanishing Spencer cohomology, and moreover, the symmetric forms are flat as left modules, respectively projective or finitely generated projective, then the holonomic jet functor preserves the flat projective and finitely generated projective subcategories. And you have the analog of the statement that the jet bundle of a vector bundle is again a vector bundle. Okay, so at the very beginning, I was saying that if you apply your constructions to classical data, you should get the classical output that you expect. Let's quickly consider why that is the case for this, because this is very different from how people classically define jet functors. So K will be the real numbers, and A will be the smooth algebra of smooth functions on some manifold with the standard exterior derivative as the differential, which takes values in the usual one forms. Just regard it as a first order differential calculus. Okay, let's take N to be a vector bundle and E to be its C infinity n module of sections. Then this diagram shows that we can construct an isomorphism between our construction and the sections of the first jet bundle. And moreover, that this isomorphism intertwines the prolongation operators. So that's an important thing. It's not enough to just have an isomorphism between modules or bimodules. You also need this isomorphism to take prolongations to prolongations. Otherwise, they are not equivalent in the sense of jets. But this holds in this case. Okay, so at least at one jet level, our construction is isomorphic to the classical one. Okay, now let's recall some old results from the 60s. So Goldschmidt showed that there is a unique differential operator which characterizes the n-1 jets. And actually on this page, I should have written sections everywhere. I'm sorry, but it may be more readable without the gammas. So this should actually be sections from the various spaces. There's a unique differential operator which has a certain symbol, which is the natural projection, and satisfies an exact sequence, and characterizes by this exact sequence the n+1 jets inside the first jets of the n jets as its kernel. Okay, and delta now is just this Cn is some complicated space once again, and delta is the Spencer differential. Okay, and the uniqueness result of Goldschmidt will be important to us because it means that we can identify the map rho from his result with our map F tilde. It's easy to see for n equal to 2 that this F tilde map satisfies all the properties of rho, and since it's unique in the classical setting, it must be the same. So this characterizes our holonomic jets as the classical holonomic 2 jets. So our holonomic 2 jets as the classical holonomic 2 jets, as submodules of non-holonomic jets. And moreover, the prolongation maps coincide both. I mean, you can make them in by the same construction, both classically and for our constructions. So this gives us the proposition that our 2 jet applied to some space of section is the same as the standard space of section of the standard jet bundle. It's isomorphic. And the isomorphism takes our prolongation to the classical prolongation. Okay, then we need one more lemma from the 60s, which is from Quillen's thesis in 64. You can write the n plus m jet as the intersection of the n jet of the m jet and the n-1 jet of the m+1 jet inside the non-holonomic n plus m jet. And these are now classical non-holonomic jet bundles of order n plus m. I wrote it in our notation because I don't know a good classical notation for this. And yes, we will use that result to construct a inductive proof, or what I call the classical correspondence. So the classical correspondence means exactly that if you take a smooth manifold and the exterior differential forms in the standard sense equipped with the de Rham differential, and let E be the space of smooth sections of some vector bundle, then the classical non-holonomic and holonomic jet bundles are isomorphic to our constructions of non-holonomic and holonomic jet bundles as left modules, respectively. And moreover, the prolongation maps and jet projections are compatible with the isomorphisms. So the smooth one forms in particular are regular enough. In particular, they are flat as a right module. In fact, more is true, they're projective and finitely generated. That we can show that in this case, Jn in our sense is equal to J1 intersected, J1 Jn minus 1 intersected with J2 times n minus 2. And combine this with the Quillen results and the base cases n equal 1 and the n equal 2 case we got from Goldschmidt, and verifying the prolongation thing gives an inductive proof of this classical correspondence result. Okay, so now let's talk about something completely different. Let's talk about linear differential operators. So let E and F be left A modules and take a k-linear map, not an A-linear map, between E and F. We call this a linear differential operator of order at most n with respect to our exterior algebra. If it factors through the holonomic prolongation operator, Jn, that is to say, there exists an A module map, which we call a jet lift, delta tilde, such that you have the following triangle diagram commuting. So it doesn't matter if you just apply the k-linear map delta, or if you go up by jet prolongation and then apply the A-linear map delta tilde. And if this n is minimal, we say that delta is a linear differential operator of order exactly n. And here are some examples of differential operators. So suppose that omega 1 is free and finitely generated as a left module, which is to say parallelizable in the classical sense. Then if you take a basis, then you can define partial derivative operators by just splitting the differential into its components in this basis, taking each component. These partial derivative operators are first-order differential operators. Okay, for left A modules, there are also a notion of left connections. This is not something that we came up with. It's in the literature in many places. And for a left connection with respect to some first-order calculus is a k-linear map satisfying this Leibniz rule. So it goes from E to omega 1 tensor E, satisfying this Leibniz rule. Left connections are also always first-order differential operators. And finally, the EV operator, which we defined via its jet lift earlier, is a differential operator which goes from the one jets to this special strange sections. And yeah, it's the defining operator of second-order jets. Okay, and we can also define vector fields. So take a first-order calculus and take the right A module of vector fields by considering the first-order differential operators, which annihilate locally constant functions. And by locally constant functions, I mean the kernel of the differential. And this comes with a right module structure, which is given by post-composing with a right multiplication operator. Right multiplication operators are, of course, of order 0, since so for these vector fields, we have a bijection between the vector fields and the A-linear maps, left A-linear maps from omega 1 to A. This is the interior product. And by introducing a slightly more complicated left action, you can make it a bimodule. And RA in this formula at the bottom is not the right action on A, it's the right action from the bimodule structure on omega 1. And you actually need to use the jet lift explicitly for this. And d is the differential of omega, of course. So these are also exempt. Okay, so we will show that the differential operators in this sense satisfy the most important properties of differential operators in the classical sense. So in particular, if n is less than m, then a differential operator of order at most n is also a differential operator of order at most m. It's very easy to see. Just apply the jet functor, the jet projection.
It's a little bit strange written differential operator of order n, yes, at most. I'm sorry, I don't understand.
Yes, it's difficult to say what a differential operator of order exactly n is because it's not a vector space, for example.
Well, that means that the operators with a lower dimension are embedded into the operators with a bigger dimension.
Yes, exactly.
Okay.
Right, so you can simply take the jet projection and then apply this to the jet lift that you already had, and then you will get what you wanted, an A-linear map which lifts delta. So this is not so difficult to prove. Slightly more complicated is to show that if you take two differential operators of order at most n and m, then their composition is a differential operator of order at most n plus m. This is maybe the most important property. So this is done by first you take the jet lift tilde 1, delta tilde 1. This goes from JNE to F, of course. But this is an A-linear map, and the jet functor is a functor. So you can apply functors to A-linear maps, and if you do, you will get a map from Jm times Jn to Jm of E and F, respectively. So this middle top arrow is just the jet functor applied to the jet lift. And then to really make this a jet lift, you need to embed the, or at least have a map from the m plus n holonomic jets into Jm of Jn. And the difficulty of this result is in constructing this map. But I mean, it's not terribly difficult, but it is some work to show that it is well defined. And when you then compose the whole upper and outer part of the diagram, you will get an A-linear map which lifts the composition of delta 1 and delta 2. And so it will really be a differential operator of order at most m plus n. The fact that you can compose differential operators mean that there's a category with the same objects as left modules and with morphisms given by the differential operators. So in particular, if you fix an object of left module, so if you fix a left module, then the differential operators from that module to itself will form an algebra under composition. And in the special case of algebras from the function from the differential operators from the algebra A to itself, we will call this D, which is kind of a standard name for this. Maybe we should have called it DA or something, but okay. Now, the algebra A up, the opposite algebra of A, embeds into D as zero-order differential operators via the right action of A on itself, because yes, zero-order operators are precisely A module maps, and right differential operators are left A module maps. But on the other hand, left multiplication operators need not be differential operators when A is non-commutative for any order. It's not necessary. It can happen, but it's not necessary. And in particular, they are never zero order unless A is central, in which case it coincides with the right multiplication operator. But we can fix that. So the question that you asked earlier is closely related and is the simplest case of a so-called what we call a terminal calculus. So if you have some element f of a, then there is a minimal first-order differential calculus for which left multiplication by f is a first-order differential operator. And we can construct this explicitly. In fact, there is a whole category of such calculi, but this inner calculus, which is defined by the differential, which is just a commutator with this f on a itself, turns out to be the terminal object in this category. Okay, and this gives us some differential relations for each element. So if you take some set of elements in A, then you can take the terminal calculus for each set and take the intersection between all the differential relations. If you consider this as differential relations for a new calculus, then we'll call this the terminal calculus for the set. So the omega 1s is the terminal calculus for the set S inside of A. And that means that all elements of A will be realized as differential operators. The left multiplication operators will be realized as differential operators. So this is actually a really good way to produce examples of new differential calculi, because in many cases you know which multiplication maps you want to be differential operators. For example, if you're doing quantum mechanics, then you know that the Hamiltonian operator should be a differential operator. Okay, this is not so important to us right now, but morphisms between calculi are unique and they're always epimorphic. So let's take an example, the first proper example of this talk. Let's take the quaternions, the noncommutative division algebra, which is generated by one ijk subject to this standard Hamilton's equations. So left or right modules are called left and right quaternionic vector spaces, and these are actually characterized by quaternionic dimension. They work more or less like normal vector spaces. On the other hand, quaternionic bimodules are not necessarily free modules over as bimodules. So let's construct the universal and a terminal calculus for the quaternions. So the universal calculus is very nice. You take a times a plus 1 times 1, and if you take the multiplication here, you get minus 1 plus 1. So this is in the kernel, and similarly for j and k. Okay, so let's consider the terminal calculus for I. We compute the kernel of the multiplication map with I interposed, and a direct computation just gives us a basis for the differential relations. You get I squared plus 1 squared, and j squared minus k squared. And you should verify that this is actually in, well, if you want, you can verify that this is in the kernel of the multiplication. You do the same for j, and since ni and nj have quaternionic dimension 2, their intersection has quaternionic dimension at least 1, and we can compute this intersection, and it will be nij, which is generated by one element, 1 squared plus I squared plus j squared minus k squared. And this will be the differential relations for the terminal calculus. So let's do some geometry with this terminal calculus to try out our construction. So first we should compute the structure equations. And if you do that using the differential relations to simplify things, you get that it's generated by di and dj as a free left module.
I'm sorry, so it looks like that you need not hyperbolic plane, but a quaternion plane.
Sorry?
It is a hyperbolic plane or quaternions.
I don't understand the question. For this, it should really be quaternions.
Okay, don't.
You mean why it is minus here?
Yes, it's a quaternion equations, properties, sorry.
Yes, but actually this construction is not conjugation invariant, so k is kind of special.
I see, sorry.
So you need this minus on the k to cancel out so that you're actually in the kernel of the multiplication. Otherwise it would be nicer, but okay. Okay, so we compute the structure equations, and you get that di and dj are generators, and you can write dk as minus j times di plus I times dj. And you can also compute the bimodule structure using this, although they define each other, the bimodule structure and the structure equations, via the Leibniz rule. So you get some non-trivial bimodule structure on omega 1d. Okay, now we want to compute differential operator. And zero order operators are from A to A now. The zero order operators are right multiplications generated by 1 and right multiplication by Ri, j, and k. And at first operator, we have partial derivative operators, which I just computed using the structure equations. And here, the column vector means that it takes the element 1 to 0, it takes the element I to 1, and so on. It's not really column vectors, it's just some notation to compactify a little bit. Okay, and the algebra of differential operators now is generated by 1, Ri, Rj, and Rk, and the two partial derivative operators by di and dj. And we can also describe the relations as an algebra in terms of generators and relations exactly. And moreover, for this particular case, the algebra H embeds into D. Li and Lj, the left multiplication operators by I and j, are first order operators by construction, and therefore their composition Lk is of order at most 2, and in fact it is exactly of order 2. Okay, so let's compute the symmetric forms. And now you get that the second order symmetric forms actually look like antisymmetric forms in the usual sense. So you get di times dj minus dj times di. But remember that this is actually symmetric. It's just symmetric in the sense of quaternions. And if you compute the third degree symmetric forms, you get 0, which means that jet dimension stabilizes. And in fact, you should expect this because it's a finite dimensional algebra. So you have only a finite dimensional space of possible linear operators on it. So if the jets are actually representing differential operators, then it has to stabilize. And in this case, it stabilizes on degree 2. You have the first jet module of H is isomorphic as a left module to H3. And J2 is isomorphic to H4, so that's their quaternionic dimension. And if you go higher, then it's stable. So Jn for n greater than or equal to 2 is just isomorphic to J2, and the isomorphism is the jet projection. And to do some geometry, we can note that S2 is isomorphic to H as a bimodule. And so omega 1 admits a unique up-to-scale quantum metric, and we can compute its Laplace operator in the noncommutative sense, and it will be 2 times partial j composed with partial I. Okay, so let's talk about symbols. Let E and F be left modules. Then we can define the symbol module of E and F by taking the quotient of differential operators at most n by differential operators of order at most n minus 1. We showed that n minus 1 embeds into n. It was one of our propositions earlier. Define this for all n greater than 0. And let's say that the differential operators of order minus 1 are just 0. We will call the space of symbols of order n. And let zeta n be the canonical projection map to the quotient. Then the symbol of a differential operator is its equivalence class under this canonical projection. So in particular, if you take a differential operator of order n, then it is actually, of order at most n, then it is actually a differential operator of lower order if and only if it has 0 symbol, symbol considered a symbol of degree n. And that's important to us. So as an abstract quotient, it has very nice properties, but we would like to describe the symbols a bit better. So let's suppose that quantum symmetric forms of degree n are contained in the submodule generated by prolongations. This property is just called, well, exactly what I just said, the generated by prolongations. If you have that property, then you have a map Rn, which takes symbols of order n into alinear maps from symmetric forms of degree n to f. And this is just given by the restriction of the of some jet lift from an element in the class of the symbol. And this is well defined and natural. And moreover, if you have exactness of the n-jet sequence, and this map happens to be, then this map happens to be injective. So in particular, R1 is always injective, and R2 is injective whenever omega-2 is the maximal prolongation, which is actually interesting because this says that, in fact, it's not great to consider other exterior algebras than the maximal prolongation. You will lose some properties every time because it's basically the only time you get this injectivity property for R2. And when R is injective, we can identify the symbols of differential operators with their jet lift restrictions to the symmetric forms of degree n. So you simply take some differential operator, take its jet lift, and restrict it to Sn inside Jn. And this can be used to measure the symbol. And this also gives us a way to identify operators which are lower order effectively amongst the higher order ones. Okay, so here are some examples of symbols of differential operators. If you take d, the derivative itself, then its symbol is simply the wedge. If you take a left connection from e to omega 1e, then its symbol is the identity operator on omega 1e. For the vector fields, you have the interior product, and that interior product is in fact an isomorphism as A bimodules to the alinear homomorphisms from omega 1 to A. And the symbol of a vector field is precisely its corresponding element under this isomorphism. So it's its interior product operator. And the Spencer operators that we discussed earlier are differential operators of order at most 1. And if m is greater than 1, then they have symbol the tensor product of the wedge and the projection, the jet projection. And as a special case, the Spencer operator Sn-1, has symbol the identity operator times the projection. So this all turns out to be very natural things, and in particular, the characterization of connections is nice. In fact, a differential operator is a connection exactly if it has an identity operator as its symbol. Okay, now we have a bimodule structure on the vector fields, and this allows us to take tensor powers, so you can consider the A tensor power of vector fields with itself. Then we have a natural pairing between omega 1, tensor omega 1, and vector fields, tensor vector fields, which is defined in terms of jet lifts by the formula near the bottom of the page. And in this formula, dot is the right action of an element of A on omega 1 d. So keep in mind that when you evaluate this thing, you will get an element of A, and then you apply the right action of that element of A to alpha. And composition of vector fields as operators, as differential operators, is k-linear and associative. So in particular, it descends to the tensor product over K. That's the, I didn't write K here, but the vector field, tensor vector field with no symbol in the tensor product is over k. So in particular for this tensor product, you can take the composition map, and for various reasons I turn it around. And in general, the composition of two vector fields will give you a second order differential operator, or rather a differential operator order at most 2. Now you can apply the symbol map to such an operator and map it into the symbols.
You are trying to show some equivalence of composition formula, yes?
Sorry?
You are trying to prove some analog of composition formula of differential operators, yes?
No, not exactly. Right now, I want to show what a Lie bracket is in this setting. So for a Lie bracket, you should take some linear combination of compositions, which is actually lower order than generically. And we will measure this by this symbol map and show when it vanishes. This will give us Lie brackets.
Okay.
So sorry, I didn't say that carefully, but let's try to construct Lie brackets in the non-commutative setting.
Well, but it's a very natural question about the composition formula.
Yes.
I think
there's also a natural composition formula for symbols, indeed. So you can consider them to be algebras if you fix the object.
Okay. Okay. Well, I have got your question, but I will ask it after your talk. Okay. Thank you.
Okay. I see that we have arrived at the end of the time. Can I keep going for a little bit longer to finish the last bit? Or?
Yes, a little bit longer, of course.
Thank you. Okay, so we want to see when a composition of a linear combination of vector fields is actually a degree 1 operator. And to do that, we use the bottom of this sequence of this diagram. We descend to the A tensor power of vector fields with vector fields, apply the natural pairing to take an A homomorphism, to get an A homomorphism from a left linear map from omega 1 tensor omega 1. And this can be restricted to S2, which is sitting in there. So you actually get something defined on the symmetric forms, but that's precisely the same space as the symbols are in, and we identify these spaces. Then this diagram commutes, in fact. And in the bottom diagram, we can take the kernel of the two right-going compositions. We call this kernel the annihilator of S2. And then you take the lift of the annihilator of S2, and this we'll call the asymmetrized vector fields. This naturally sits inside the K tensor product of vector fields. Now, the proposition is if your linear combination of composition of vector fields comes from these asymmetrized vector fields, then in fact their composition is again a vector field, or in other words, a order 2 operator. And the proof, the sketch of the proof is basically what I was saying. The composition is of order at most 2, but if the second order symbol vanishes, then it's actually of order 1. And therefore, when it's in this annihilator and the diagram commutes, the order is exactly 1. It cannot be of order 0 because the vector fields annihilate the kernel of D. Unless it's the 0 operator itself, of course. It could commute. Okay, so this gives us a definition of Lie brackets. Let pi asim be a projector, or more generally a linear map into asim from the tensor product of vector fields. And then you take a map of the form composition of pi asim of y tensor x. This will be the Lie bracket of x and y. And there are lots of examples of these things. For example, commutators from differential geometry, supercommutators from supergeometry. You get natural ones for Clifford algebras and quaternions via orthogonal projectors. You can do this for finite group algebras at least, maybe infinite group algebras too, although we haven't tested it. And you can do it for some quantum geometries via the braiding. So let's revisit the quaternion example. The vector fields can be written as sums of partial derivatives with quaternion coefficients. And we compute the kernel of the projector pi asim. It's spanned by this element, delta partial I times partial j minus partial j minus times partial I. And you have to apply this complicated map SH to it, unfortunately. Where right, something complicated. Okay, but in the end, you can compute Lie brackets of quaternionic vector fields if you want, and there are a couple of examples at the bottom of the slides. All right, this is the last thing that I was expecting to have time for, but if you want more, there's this bonus about higher connections and curvature. So what do you think?
I think that it's enough for today.
Okay.
We can meet another time.
Very good.
And wow, I have got a little question to you.
Yes.
I'm not sure that it will be little, but anyway, did you think about calculating of index of the operators which were defined above? Because if you have got a composition formula, then you have got a node, you have got a symbol, so you have got something like a symbol calculation. So you can, in the same way as for pseudo-differential operators, you can define something like parametrics or quasi-invertible operator. You can look on calculating of index and so on, but you will need the trace for that, I think. But anyway, did you think about that, or it's something which is not from your area of interest?
I haven't tried to do this yet. No, it's certainly an interesting question. It depends on whether we can find a tractable way to define and then compute things, which I don't know. I haven't tried. So that's my answer. Sorry, short answer to a long question.
I'm afraid that there is an intermediate problem. Before defining index, you should define the pseudo-differential operators. And this is not quite as simple as for the classical case.
Ah, yes. No, I don't know what the definition of pseudo-differential operator should be either.
Well, they can try to calculate index for differential operators. It's so I don't see the easy way to define pseudo-differential operators, but if they have got a simple calculation for differential operators, because they can try to find that formula without giving a definition of pseudo-differential operators. So, well, okay.
But
anyway,
you need the parametrics. And that's why you need invertibility model or something. And this is really, you need to define something like an algebra of pseudo-differential operators.
So, sorry, invertibility of what?
yes, perhaps.
Invertibility modulo some ideal. If you want to find an index, and this invertibility would require something like pseudo-differential operators.
I see. Okay.
I think that even inverse symbol, if it exists, is not within this framework. So roughly speaking, it's a rational function, and yeah.
So if you deal with a Laplace operator, for instance, then its symbol will just be the metric itself. So maybe you can do something with that. I don't know.
Yeah, very interesting. Any other questions to Henrik?
May I ask one more question? There is a lot of examples of non-commutative spaces, like like non-commutative torus, which is defined by an irrational rotation algebra, quite a lot of other non-commutative spheres and so on. So how does your theory works for these examples?
So it works just fine. I mean, we haven't used any assumptions that are not available on this basis. In particular, you can compute things on, for example, quantum SU2 with the three-dimensional calculus, or on non-commutative torus with the standard calculus, or something like that. In practice, the main problem is to describe the space of differential relations in these cases, which might be complicated. But in this, this is an area of active research, but so far it's going well.
So have you at least for calculated, at least for one example, maybe the simplest is the non-commutative torus, have you done all the calculations which can be done for this example?
Not all, no.
Okay, thank you.
Any other questions?
Was this published somewhere, this non-commutative torus, using your formalism?
No, it's not published somewhere. So it depends on what you mean by published. If you mean published in a journal, then it's still in review. If you mean it's available online, then our paper is on the archive, but the non-commutative torus is not in there. It's on some papers on my right on my desk.
Okay, thank you. Maybe one more question. There is, in recent years, activity, say, non-commutative geometry and index theory of hyperelliptic operators, say, on contact manifolds or something similar. They have interesting notion of symbol. Did you think about applying your ideas, or at least is their symbol a special case of yours, or did you think about this relationship?
Could you describe more exactly which setting you're talking about? If it is what I'm thinking about, then yes, it's a special case, but I'm not entirely sure what you're asking.
Yeah, for instance, on the Heisenberg group, hyperelliptic operators are not elliptic, but still they have good symbols and index. Roughly speaking, different vector fields, even though their usual order is, say, 2, but their I would say Heisenberg order is 1. So just a special choice of orders coming from contact geometry.
So okay, so it's classical examples.
I wouldn't say classical. No, of course they are differential operators, but there is a special filtration of this say tangent bundle, or what Hermander had operators as sums of squares or something of this kind. So these are, in the usual sense, differential operators, but their order has to be counted in a different way. Coming from geometry. In Russia,
it's weighted differential operator, so it's probably can be incorporated in the scheme, but not directly. That's weighted differential operators.
No, but if you wanted order to be different, then that is something that we can do using the terminal constructions. You can take some operators that you want to be differential operators. If you know what their order should be, you can compute the appropriate terminal calculus, and then you will get some geometry in our sense where, in fact, these operators have that order as their actual order. And it would be surprising to me if the notions of symbol are different, but this is the first time I hear about it, so I have not tried it, of course.
Thank you. Any other questions? I will stop the record.